Okay, so let's start. Marius is not in the room, so I'm going to do something completely unethical, and I'm going to make some advertisement for the European Math Society. So I don't know how many of you have heard about Horizon 2020. Does anyone knows about that? Horizon 2020. So that's one problem. So that's the next. So maybe you have heard about framework program number 6, 7, 4, 5, whatever. So that's the next funding program for the European Union. That's going to determine much of what you do in the future. No one knows about that. You should know about it. Otherwise you won't get money to do research. So one possibility is to join the European Math Society, which is something that collects all the math society in Europe. Of course you should be a member of your own math society in your country. Get involved. Alright. So much about politics, now math. And you just go to the web and look for European Math Society. Of course, that's what we do nowadays. It's not very expensive, like 22 or 23 euros per year, the membership. So, anyway, so last time I tried to show you mainly through examples, a few problems, through global problems that arise in Poisson geometry. So now we want to develop some techniques to deal with these. So the first thing that I should say is that the way that we dealt with Poisson brackets last time, which was a bracket on the space of functions, is not the most efficient way. It's better to use tensor fields. So that's easy. So if I start with a Poisson bracket, there is another way of describing the same gadget, which is through a bivector. So that's a section of the second exterior product of the tangent bundle. So you are used to two forms. This is the dual object. And remember that, so this was a Lie bracket, so in particular was skew-symmetric, bilinear, and it satisfied the Jacobi identity, the Leibniz identity. And also the Jacobi identity. So the first three properties, skew symmetry, bilinearity, and Leibniz, are completely encoded by a bivector. So pi, and the way to go from one to the other is simply by evaluating on functions. So if I give you the bracket, you get the pi. If I give you the pi, you get the bracket. Right? So the last one is not satisfied in general. If I give you a bivector and define the bracket in this way, it will satisfy these three properties. It will not satisfy the last one. So there is some nonlinear PDE that has to be satisfied, and Poisson geometry is really about this nonlinear PDE. And this nonlinear PDE can be written in a shorthand in this form. And there is an operation here. So this thing here stands for the Schouten bracket, and this is Holland. Schouten was Dutch. I don't know how to pronounce Schouten. Schouten. You're not Dutch. Okay, so what is the Schouten bracket? That's not mysterious. That's just a bracket on so what is a multi-vector field in local coordinates? It's some gadget that looks like some coefficients, and then here you have something like that, right? So it's like a higher version of a vector field. So the Schouten bracket just generalizes the usual Lie bracket of vector fields, and it has to satisfy the obvious properties. So I'm not even going to write the obvious process because I'm not going to use much the Skelton bracket. And I want to get to other things. So, Skelton bracket of two multi-vector fields. Okay, so write it this way. So if I have a multi-vector field of degree k, a multi-vector field of degree L, the Skelton bracket is going to be a multi-vector field of degree k plus L minus 1. Okay? And, well, it has to satisfy, so it's plus natural properties. Okay, so this is a much more efficient way of describing multi-vector fields. Okay, I don't want to go to this blackboard yet. Okay, now using this pi, you see immediately that we have a way of going from the cotangent bundle to the tangent bundle by contracting. So if I have here a covector, I contract and I get a vector. So there is a bundle map from the cotangent bundle to Tm. We already saw this somehow when we said that to every function we associated a vector field. That's, in this notation, that's going to be pi sharp of df. Okay? So this is a linear map at each point from the cotangent space at that point to the tangent space at that point. This linear map can have range with varying dimension. Okay? So we call the rank of the Poisson structure at the point x, by definition, is the dimension of the range. So pi sharp image pi sharp x. Okay? So of course, if you choose local coordinates, then the pi is going to have some expression like this. And the rank, so of pi at x is simply the rank of the matrix pi ij x. And this doesn't depend on the choice of coordinates. Now, this pi ij is a skew symmetric in the I and j. So if you switch I and j, it switches signs. So that implies that the rank is always an even number. Okay? Alright, so now here's the first theorem in Poisson geometry. It's called the Darboux-Weinstein theorem. It says that let x naught. So from now on I will write m pi to denote a Poisson manifold, a manifold with a bivector which satisfies this condition, which is the same thing as a manifold with a Poisson bracket. So let's fix a point and assume the rank at that point is an even number, so let's say it's 2L. Then the theorem states that there exists local coordinates Q1, QL, P1, PL, Z1, ZS, centered at this point. So when I say centered at x0, it means that the values of these variables at x0 are 0, such that our Poisson tensor is written, so at the point x, well, okay. So it has a part which is a symplectic part, and another part which is a purely Poisson in some sense. So we'll write this as maybe J less than K. So only depends on the z coordinates, and this part has the property that at x0, so that corresponds to 0, zeros, it vanishes. Okay? So this is saying that locally every Poisson structure splits as a product of a symplectic one with one which vanishes at the point. Okay? And these, you cannot say much about these functions that appear here. The only thing you know is that these functions at the point 0 are 0. Okay, so locally you have symplectic times Poisson vanishing at x0. So locally at x0. Alright? Okay, so So this is the first basic thing about Poisson manifolds. So let's discuss this a little bit. So first let's just give a sketch of the proof. So the proof is by induction on the rank at the point x0. So first, step 1, if the rank is 0, well, if the rank is 0, there is nothing to prove, because if the rank at x0 is 0, then that means the Poisson tensor vanishes at the point. So any coordinates that you choose, this part will not be there, and it will have just this part. Okay, so we can assume that then this is obvious. So let's assume the rank is greater than 0. Now if the rank is greater than 0, then we can choose a local defined function around x0, which I'm going to call P1, such that the Hamiltonian vector field associated with that function at the point x0 is non-zero. Okay? Okay, now if I have a vector field which is non-zero, I can try to straighten it out. So then we can find let's say coordinates. Let me use the same notations I have in the notes so that I don't make a big mess. So then we can find let's say a local function Q1 such that when I compute these vector fields xp1 on q1, I get 1. Okay? So this is done by straightening out this vector field. Okay, but then, if I look at the vector field q1, and I compute its bracket with the vector field associated with P1, then by this exercise that we just saw, the first exercise in my lecture, this is, well, that was in the symplectic case, but in general this is true for any Poisson manifold. So this Lie bracket is the bracket associated with the Poisson bracket of these two functions, but this is the same thing as P1, the bracket of P1 with Q1. So this is 1, and the Hamiltonian vector field associated with the constant function is 0, so this is 0. So these two vector fields commute. So if I have two vector fields that commute and which are non-zero, I can choose coordinates completing these P1, Q1. Let's call them x2 up to xn, such that these vector fields preserve these coordinates. Okay, so for I from 2 to n. Now, don't ever forget that this just means the bracket of Q1 with this function xi. This is the bracket of P1 with the function xi. So we already know that the brackets of the xi's with the Q1 and the P1 is 0, right? So the only thing that we missed is to compute the brackets of the xi's with xj's and see that they don't depend on P1 and Q1. Okay? So that's a simple computation. So if I do it here, since people so let's start with this one, for example. So let's look at this gadget. So these are both 0 because this we know it's 0. But now by Jacobi identity, this is the same thing as xi, xj with P1. Right? So this is the same thing as, because we know that all the brackets of xi's with P1 are 0, the only thing that it's left is the bracket of P1 with Q1. And bracket of P1 with P1 is 0 because of skew symmetry. So this is the Q1 bracket of Q1 with P1, which happens to be minus 1. The bracket of P1 with Q1 was 1. So the bracket of Q1 with P1 is minus 1. So we are saying that 0 is this. So this is 0. So this function that we have here does not depend on Q1. And a similar computation where you change the Q1, where you change the P1 to Q1, you go through it, will give you that this bracket does not depend on P1. Okay? So, similarly, with Q1 switched with P1, so this is a function, this only depends on xi's. Alright? So you split apart one symplectic piece, this P1, Q1. And now you can use induction to finish the result. Okay, so that's the Darboux-Weinstein theorem. And here is a nice exercise that maybe we'll discuss tomorrow So I'll choose 2 exercises from today's lecture to discuss tomorrow. So this is exercise 2. And yesterday at dinner we were cooking up a name for these things that are going to appear in this exercise. So in the literature, the Poisson structures that I'm going to talk about are either known as log Poisson structures or B Poisson structures. So I'm going to call them blog Poisson structures. Okay? Just to be politically correct and not upset neither community. So a blog Poisson structure is a Poisson structure so I should say here, so this is either a log, symplectic, or a Ness Poisson structure. That's what you find in the... Okay, so this is a Poisson structure pi on an even dimensional manifold such that when you take the top power of your bivector, so the top power, that's going to be a section, so a map from M to the top power of Tm. Okay, this is a line bundle. Right? It has a zero section. So I'm going to require this map to be transverse to the zero section. That's the only condition. Okay? Such that this is transverse to zero section. Okay, then, since that's transverse to the zero section, we can define Z to be the inverse image of the zero section, and that's a submanifold of M. Okay? A codimension 1 submanifold. Okay, so the exercise is show, well, first, that's the trivial part. If you take a point outside this zero set Z, so then we have Darboux coordinates. Well, that's trivial because outside that the pi was going to be symplectic. And if you take a point in the zero set, then we can choose coordinates x, y, p2 up to p2, q2, p and qn, such that this pi is going to have a part which looks like this, and then the symplectic part. Okay. And you should be able to prove this using just this Darboux-Weinstein theorem. Okay? Up there. Right? So that will be for tomorrow's exercise session. Okay? Alright. Okay, now I would like to talk a little bit more about the splitting. So I'm going to introduce a concept which is quite important, which is the right notion of path in Poisson geometry. So now we are going to start talking about a subject which may be called contravariant geometry, which is kind of the underlying theme in this lecture. So here is a definition. A cotangent path is a path in the cotangent bundle so I will denote the interval 0, 1 by the letter I. So we take a path and it satisfies an extra condition. So what is the extra condition? Let's see. We have a Poisson tensor that gives us a way of going from cotangent to tangent vectors. And now I'm saying that I have a path in here. Right? So I can compose with pi sharp and get a path in the tangent bundle. Or I can first project down to M and get a path downstairs in M. And now I'm going to require that if I take the derivative of this base path, which is going to be something in here, so take the derivative, it has to coincide with that. Okay? So, cotangent path is a path in the cotangent bundle such that pi sharp of A of t is the derivative of the base path. So I should have said P is the projection in the cotangent bundle. Okay? So this is like giving a path by giving its derivative in some sense. Except that here we don't work in the tangent bundle, we work in the cotangent bundle. We'll see, I will try to convince you that this is the right notion of path in the Poisson geometry world. Okay? So just as a simple example of producing cotangent paths, if you take a Hamiltonian vector field and you take a trajectory of these vector fields, then if you compute the differential of the function, the Hamiltonian, along this path, that's a cotangent path. That's very easy to check. Okay, now I'm going to use cotangent paths to show that this symplectic factor that appears in the Darboux-Weinstein theorem actually has a very concrete realization. Okay, here it just looks like it depends on some choice of coordinates, blah blah blah. Maybe if we choose different coordinates we get a different factor. That's not the case. So, proposition. So let's use these cotangent paths to define an equivalence relation. So I'm going to say that 2 points in my manifold are equivalent if I can find a cotangent path that starts at one point and ends at the other point. Now, when I say what is the initial point of a cotangent path? Cotangent path is a path in T star M. So for me, the initial point is you look at the base point and it's is T equals 0 for the base path, right? So maybe I should say that before the proposition. So for a cotangent path, the initial final point are P of A0, P of A1. So if later I say a cotangent loop, what I mean by a cotangent loop is a cotangent path whose base path is a loop. Starts and ends at the same point. Okay? Okay, so the proposition is the following. Define x to be equivalent to y if there exists a cotangent path, starting at x and ending at y. Okay, then the equivalence classes of this relation are in general only immersed submanifolds, but they are symplectic. And the inclusion, so I have such an immersed, this is an equivalence class, it has a symplectic form, and the inclusion of this immersed submanifold in M, since this is symplectic, it has its own Poisson bracket, the inclusion is a Poisson map. So that's what's called a Poisson submanifold. In this case, it's a symplectic Poisson submanifold. Okay. So let me make some remarks about this and relate this with the Darboux-Weinstein theorem. Yeah? You want to put this... So remarks. So let's fix such a leaf. We're going to call it symplectic leaves, these submanifolds. Okay, so first thing, if you look at its tangent space, so I guess I should write, I want to be very pedantic, I should write it maybe in this way. So that's the image, so that's the tangent space to this leaf. So that's equal to the image of pi sharp at the point x. In other words, if we think of the assignment that to each point of the manifold M assigns the image of pi sharp, this is a distribution, so it's a varying, continuous or smoothly varying choice of subspaces, but be aware that these dimensions can vary. Okay? And what we are saying is that these S's are integrable leaves of this distribution. So is an integrable, I should say generalized. The generalized just means that the dimensions vary distribution. Okay, the second remark is that actually these S's, they have better properties than just generally immersed submanifolds. So if you take such a leaf, you have the inclusion. Okay, let me write this maybe this way to follow the note. So I have the inclusion. Now, if I take any other submanifolds and a map, any other manifold and a map, and if I assume that phi of n is contained in S, then to check that this map is smooth is enough to check that the induced map. Maybe I should draw this. That this induced map is smooth. So this is much better than usually immersed submanifolds where this fails. Okay. So phi is smooth if and only if phi bar is smooth. Well, in one direction it's always true, but the point is in the. So if phi bar is smooth, it's obvious that phi is smooth. The point is the other way around. Okay. Okay. Anyway, so.
Sufficient to stick just with integral curves of Hamiltonian fields to get these.
Yeah, so there's another way, yeah, sure. Good question. So you can also define these symplectic leaves by looking at paths, which are solutions of Hamiltonian vector fields. So there is a point that I'm not making very precise. So if you do that, it's clear that you better choose piecewise smooth paths. So you better choose paths made of components which are integral curves. It makes your life much easier. So here I didn't say anything, but I'm considering cotangent paths that are C1 map. So these are a C1 map. Okay? And actually here I don't need to assume piecewise C1 maps, but you can assume piecewise C1 maps if that makes your life easier. Okay? But there's a bunch of technical things that I'm not. Right.
So is there an example that you can come up which is not Hamiltonian for a cotangent path?
Yeah, sure. Okay. Okay. All right. So the conclusion from this discussion is that this symplectic factor has a canonical representative, which is this symplectic leaf. So I have my point x naught. I have the symplectic leaf through that point. Okay? And that's when I look in the neighborhood of this point, the Darboux-Weinstein theorem says that this splits as a product. And this is a natural representative of the symplectic part. Now what about the other part? The part, this Poisson tensor that vanishes at x naught. What can we say about that part? So that part, it's slightly more tricky. And I will set this as an exercise, which is blue. So that's exercise 4 in my notes. So it asks the following: let n be a submanifold of a Poisson manifold that satisfies the following two properties. So the first one says that if I take all covectors that vanish on Tn and I apply the Poisson tensor, then this never meets the tangent to n except the 0, 1, of course. And the second condition says that the covectors that annihilate Tn and the covectors that are in the kernel of this pi-sharp map is only the 0, 1. So this should hold for every x in n. So I give you some manifold which satisfies these two properties. Then the exercise is to show that there is a natural, meaning doesn't depend on choices, induced Poisson structure on N. Now, so I should say that sometimes these manifolds are known as cosymplectic. N is called cosymplectic submanifolds. I think it's a very bad name, but it's called just to. So I give you a hint on how to solve this exercise in the notes, but let me comment a little bit on this. So the first condition, what it says, or what it implies, is that the submanifold N is meeting all symplectic leaves transversely. Okay? So one implies that N intersects. Well, what it says is that N intersects the image of pi sharp transversely, but these symplectic submanifolds are the things that integrate the image of pi sharp. So the tangent space is the image of pi sharp. So N intersects symplectic leaves transversely. So that means that N is itself a collection of submanifolds, the intersection with the symplectic leaves that it meets. Right? But now, N intersected with a symplectic leaf, you get a submanifold of a symplectic leaf. Right? So there is an induced closed to form. You pull back the symplectic form to this submanifold. So N is a collection of submanifolds, each comes with a closed to form. There is no reason why this closed to form should be non-degenerate. The second condition is guaranteeing that it is non-degenerate. Okay, so second condition implies that N intersected with an S is a symplectic submanifold of S. Okay? So now N is really a collection of submanifolds, each carrying a symplectic form. Right? Okay. So I don't have time to go into direct structures, but a direct structure is like a Poisson manifold, except that the symplectic leaves, they do not have a symplectic form anymore. They have a closed to form. So you relax the non-degeneracy condition. And what's going on here in this exercise is that there is a direct structure associated with this Poisson structure. You pull it, direct structures sometimes can be pulled back to some manifolds, and then this turns out to be a Poisson structure, this direct, pull back direct submanifold. Anyway, so that's the exercise. Okay, so using this exercise, suppose now I fix attention on a suppose now I fix attention on a specific symplectic leaf, and I take a submanifold transverse to this symplectic leaf. What can I say? So, fix the symplectic leaf, and choose N submanifolds let's put it such that okay, so you have here your X naught, you have your S, and now I've chosen here some N. So the only condition that I'm imposing it at x naught, that you have this direct sum decomposition. So that automatically implies that condition 1 and 2 are satisfied at the point x naught, right? So this implies that 1 and 2 are old at x naught. But those conditions are open conditions. If they are satisfied at a point, they are satisfied in the neighborhood of a point. So this implies that 1 and 2 hold in the neighborhood of x naught. So that means that there exists a neighborhood here where the intersection of n with this neighborhood has an induced Poisson structure. Okay? So there exists a neighborhood U such that n intersecting with U has Poisson structure. So that's a representative for this transverse factor to the symplectic leaf that appears in the Darboux-Weinstein theorem. But you see that I can choose here many n's, and they will all have an induced Poisson structure. And by the way, this Poisson structure vanishes at x naught. Okay? So, if I choose two of these, how do they differ? And I can even choose another point, maybe. And choose here another factor. Okay, so that's proposition. Let's take it maybe in this way. So maybe I'll call this a theorem because I call it a theorem in the notes and it's actually important. So let's write this. Fix a symplectic leaf. And N1 and N2, two transversals 2s at point, say, x1 and x2. So the proposition says that you can find neighborhoods U1 of x1 and U2 of x2 and a Poisson diffeomorphism phi from U1 intersected with N1 to U2 intersected with N2. So although there is no canonical choice of this transverse factor, any choice will give you Poisson diffeomorphic objects. So this transverse Poisson structure is well defined. It's up to Poisson diffeomorphism, up to equivalence. Okay, so I think I will not go into the proof of that because I'm running out of time quickly. The proof is sketched in the notes. And I did it again. I'll just say that if you go to the blog Poisson structures, the exercise that I gave you example. So for a block Poisson structure, now maybe I should call it a block symplectic structure. So let's call it a symplectic. Pi. We saw that we could write this in this form. Right? So what is going on here? Well, I think I didn't mention, but the Z, the inverse image of the zero section, that's in these local coordinates is written as the set x equals 0. So what do we have here? We have a codimension 1 submanifold, Z, which I'm going to write this way. Outside Z, this is symplectic. So the leaves of this block Poisson structure are the complement of Z, which may be connected or disconnected, right? And which is symplectic leaf or symplectic leaves. The connected components will be symplectic leaves. And then you have Z. And on Z you have a codimension 1 that's foliated by codimension 1 in Z or codimension 2 in M submanifolds, which are symplectic leaves. Right? So if I fix a point in Z where I have these local coordinates, this is the transverse Poisson structure. Okay? So in this example, it's easy to describe what is a transverse Poisson structure. In general, it's hard to describe what is a transverse Poisson structure. So, for example, for linear Poisson structures, the symplectic foliation, as it was kind of hint at Anton's lectures, the symplectic foliation is the coadjoint, is the foliation given by the coadjoint orbits. So you saw in Anton's lecture that there were symplectic forms on these coadjoint orbits. So even in this case, if you pick a leaf which is singular, meaning a leaf where the dimension of the leaves, nearby leaves, are different, it's hard to figure out what is the transverse Poisson structure. And there are various results about it. Okay? You may want to try something like SU3. SU2 is too easy, but SU3 just to check if you can find the transverse Poisson structure, the dual of SU3. Okay. Okay, so this basically finishes the local description of Poisson structures, and I promised that we should do global Poisson geometry. But already here there are some hints of global things, this symplectic foliation, and we use these cotangent paths. Now this cotangent path is just the first instance of something that happens in Poisson geometry, where you have to play the game of replacing the tangent bundle by the cotangent bundle everywhere. Okay? So here is what you usually do. In ordinary geometry, you have the tangent bundle, right? Sections of the tangent bundle are vector fields. On the space of vector fields, you have the usually bracket, which satisfies a Leibniz type identity. And you usually look at differential forms, so sections of the dual bundle to Tm, right? Or exterior powers of the dual bundle to Tm. And differential forms are useful because you have the Durand differential, and I wrote down the usual formula for the Durand differential, and that gives you, for example, the Durand cohomology, which gives you information about the global behavior of your manifold. So you can mimic this for Poisson manifolds. So for Poisson geometry, now you're going to have the cotangent bundle instead of the tangent bundle. So what's going to play the role of the vector fields are the one forms. And indeed we already saw that there is a bracket on the space of one forms, the last lecture. Or maybe we didn't. Now I think I'm mixed up. Okay, but there is a bracket. The bracket is this bracket. By the way, I think I missed a sign in one of the notes, so check the sign, please. So that's the bracket. And this bracket satisfies a property analogous to these Leibniz identities. So if I multiply one form by a function, and then I compute the bracket, you will see, using this formula, that you have the following identities. So here I have to make the one form alpha into a vector field using the contraction with the Poisson tensor. So I can act on the function f. Okay, so Lie bracket is on one forms. Now what used to be differential forms, sections of the dual bundle, now are going to be sections of the dual bundle to T star m. So it's going to be sections of Tm. So that's multi-vector fields. Okay? And there is going to be a differential called the Poisson differential, Poisson-Lichnerovich differential. So that's going to make the multi-vector fields into a complex. And the formula is almost identical. So if I have a multi-vector field of degree k, the differential is the multi-vector field of degree k plus 1, so I have to say what it does on k plus 1 forms. And again you have the same kind of formula. The only thing is, whenever you have to act by a one form, you have to first make it into a vector field, so you use the Poisson tensor. Okay? And when I have the bracket, I have the bracket on one form, so I can just the same type of formula. So just like the Durand differential, this is a differential, so d squared is 0. So you can use this to define a cohomology, which is called the Poisson cohomology. Very nice. Everything looks like it works. That's the good news. The bad news is that this cohomology is very bad. There are no techniques to compute it. So unlike the RAM complex, which is so-called elliptic complex, and that has all kinds of consequences, like cohomology is typically finite dimensional, this is not an elliptic complex in general. Okay? And so, God help you if you have to deal with it. However, this is still very important. Why? Because there are cohomology classes that have a geometric interpretation, and that's where they live. They live here. Okay? So you have to deal with this object because objects that you want, certain classes that you want to define, that's the natural world where they live. You cannot understand the whole world, but you can understand some classes that live in here. Right? So how much time do I have left? Minus. So I'm going to stop here. So next time, so this is, I only got into page 6 of this lecture. That's nice. So next time we'll continue discussing this. What we are going to see, what comes next, is, well, first I'm going to just to show you a very, very simple example of a class that lies in here and that already has a very nice geometric interpretation, okay, which is called the modular class. And then I'm going to go forward with this analogy between ordinary geometry and Poisson geometry, and this is for you to think. So remember, behind here there is also another thing, which is homotopy of paths. Right? Now I told you that there is some notion of path in Poisson geometry, which is this cotangent paths. What is homotopy of cotangent paths? Okay? And that's a really very deep, one of the deepest things in Poisson geometry that you really have to understand if you want to do global Poisson geometry. Okay? So the next lecture will be basically about homotopies of cotangent paths and, if you want, the Poisson fundamental group. Right? Okay, so continue tomorrow.